Hello, this is John Miyares, and in this lesson, we're going to be looking at the first section in Chapter 12, where we will introduce sequences and series. This section is very different from what we did before, and in fact, what you're going to see is that many of the topics that we're going to cover in this course really are a virtual hodgepodge of topics that don't necessarily build on one another. So even though this is Chapter 12, you don't need to be an expert in the content from Chapter 11 to make sense of this. I also personally find this to be one of the easier topics we will cover in this course, so I wanted to have it be one of the first topics we taught here so that you could get used to the system and the flow of this course without having to learn a really hard topic. After we get through some of the sections in Chapter 12 and take a quick excursion to one section of Chapter 14, we will go back to Chapters 5, 6, and 7 to cover the core course material, which will cover the trigonometry topics, some of which are easy, but a number of which are quite hard. So I'd rather we ease our way into those topics and perhaps let people get some solid footing grade-wise before we start tackling the hard stuff. With that, let's get started. What is a sequence? Well, simply put, a sequence is an ordered list of numbers. It can be infinite or finite in nature, and it may or may not have an associated pattern with it. Here are some examples of some sequences shown below. In some ways, you can think of sequences as functions whose domains are natural numbers. Typically, we do not use functional notation like a of n to describe them. To that end, we typically will use a subscript notation like a sub n. It is also common to put the list of numbers in the sequence in braces and separate the values by commas. The three dots at the end imply the pattern in the sequence is going to continue without bound, making them infinite sequences. Let's look at an example on how to interpret the notation. Using the implied pattern, determine the next three values of the sequence, then create a formula to describe the nth term of the sequence. Here's a sequence which I am labeling a sub n. To describe any element in this sequence, I want to use a subscript value, which I will call the index, to give an indication as to where we are in the list. The first element in the list is 3, so I'm going to write a sub 1 equals 3. The second element is 6, so I'll write a sub 2 equals 6, and so on, and so on. When I look at the pattern, I see two things. All of the values are multiples of 3, so each element in the sequence is 3 more than that came before it. This means that when I want to find the next three elements of the sequence, I can just look at the pattern and add 3 to each element that came before it, making a sub 6 equals 18, a sub 7 equals 21, and a sub 8 equals 24. From here, we have to try to figure out a formula to describe the nth term of the sequence. And when I say the nth term, that means I don't know what particular number. It could be the 5th, the 6th, the 7th, the 10th, 20th. So an arbitrary value of n would be the nth term of the sequence. The first approach we will use is called the implicit approach, where the formula we design will imply how we get from one term to the next, essentially following the pattern. In this case, what we can see is that each term is 3 bigger than the term that came before it. So we could write this as a sub n equals a sub n minus 1 plus 3. The notation implies that the nth term in the sequence will be 3 more than the term that came before it. However, when we define the rule for a sequence implicitly, we always need to include where we started from. Otherwise, eventually, if we say the next term is 3 more than the one that came before it, and if we don't know where we started from, we won't know what comes next. But in this case, we can then use this rule to find the ninth term of the sequence to say that it is 3 more than the eighth term, which gets us 24 plus 3 equals 27. For the 10th term, we can do the same thing, just adding 3 to the ninth term, giving us 27 plus 3 equals 30. The drawback to this process is that if we wanted to find a number really far along in the sequence, like let's say a sub 50, we'd have to compute all of the previous 49 terms of the sequence before we could calculate the 50th. This can get very time consuming. So in the alternative, we can define the sequence explicitly, which means we have a direct formula that will help us get to the nth term of the sequence right away. For this one, it's easy to see that the explicit formula can be defined as a sub n equals 3 times n, because every element in the sequence is a multiple of 3. This way, to get to the 50th number, we can just take 3 times 50 to get 150. Let's try another example. Here is the second sequence we were presented back on slide 2. The instructions are the same. Determine the next 3 values of the sequence, then create a formula to describe the nth term. As we list off the terms, we can use the subscript notation to identify the first 5 terms. This pattern suggests that each term is 2 more than the one before it, which would make a sub 6 equal 11, a sub 7 equal 13, and a sub 8 equal 15. The implicit rule then would say that the nth term, or a sub n, is going to be 2 more than the term that came before it, a sub n minus 1. So we can write our formula as you see here. We must also specify the first term in the sequence, a sub 1, as 1. So we know where to start from when following the pattern of skip counting by 2's. Continuing, we can see a sub 9 will equal 2 more than a sub 8, giving us 17, and that a sub 10 is going to be 19. The explicit rule of this one is a little bit harder to find because while with each value in the sequence going up by 2, they're not all multiples of 2. If we just said a sub n equals 2n, that would give us a pattern of 2, 4, 6, 8, 10, which are all 1 unit bigger than the values of the sequence that we want. To correct this, we can simply subtract 1 from the 2n to give us our final result. If you want to check this, you can plug in some values in for n to see what works. For example, 2 times 1 is 2, minus 1 is 1. Jumping higher in the list, say we wanted the 7th term, we could take 2 times 7 equals 14, minus 1 is 13. Finally, going further, if we wanted to get the 50th term, we could just take 2 times 50, which is 100, minus 1 equals 99. Now, both of the sequences we've looked at in these two examples are referred to as arithmetic sequences, which we're going to explore more in section 12.2. The idea with arithmetic sequences is that they have consistent skip patterns from one term to the next, or what we call a common difference that is going to be added every single time to each term. These tend to be some of the easiest to work with. The third sequence we're going to look at here is not an arithmetic sequence. We should be able to quickly see that the skip pattern is not consistent from one term to the next. There is a pattern, though, that you may be able to see here. To find the pattern, let's first list off the individual terms. We have a sub 1 equals 1. We have a sub 2 equals negative 3. We have a sub 3 equals 9. A sub 4 equals negative 27. And a sub 5 equals 81. What I'm hoping we see here is that each term is being multiplied by negative 3. To get the term that comes next, which would be a sub 6 equals negative 243, all we have to do is multiply a sub 5 by negative 3. Repeating this process will give us a sub 7 equals 729, and a sub 8 equals 2187. From here, that suggests our implicit rule will be a sub n, the current term, equals a sub n minus 1, the term that came before it, times negative 3, with the first term in the sequence being the number 1. This is going to make a sub 9 equal 6,561, and a sub 10 will equal negative 19,683. The explicit rule is created by realizing that we're working with repeated multiplication of the number negative 3, and that the first element of the sequence is going to be 1, the second element of the sequence is going to be negative 3. It looks like all the powers of 3 are going to be off by 1. So what we can do is subtract 1 from the power of negative 3 that we want to raise. So we can have a sub n equals negative 3 to the n minus 1 power. Seeing how this is going to work, let's look above at a sub 8. Using the explicit rule, that would give us a sub 8 equals negative 3 to the 7th power, which comes out to be negative 2,187. If we wanted to go higher, we could see that a sub 15 would be negative 3 raised to the 14th power, which comes out to 4,782,969. This particular sequence, where you are multiplying by a common factor or a common ratio to get from one element of the sequence to the next, is called a geometric sequence. And those kinds of sequences are the focus of section 12.3. Here's one that's a little bit different. Same instructions, but this time the pattern is much less obvious, not just because we're working with fractions, but because there isn't a common difference or a skip pattern, and there isn't a common multiple or common ratio being multiplied to get from one term to the next. What we have is a sequence that the first term is 1/3, the second term is 1/2, the third term is 3/5, the fourth term is 2/3, and the fifth term is 5/7. Now, you might be thinking that this is a sequence without a pattern, so we're not going to be able to write an explicit or an implicit formula to get from the nth term to the next term. But the fact that we have the 3 dots there suggests that there is a pattern that can be found. Here's the trick. What I want to do is rewrite the fractions using an equivalent form, so that while I can write a sub 1 equals 1/3, I want to rewrite a sub 2 equals 2/4. Then a sub 3 will keep as 3/5, but a sub 4 I want to rewrite as 4/6. I'll still keep a sub 6 equal to 5/7, but as I'm looking at this, I hope you're seeing the pattern by now. When I write it like this, you can see the numerators are always increasing by 1 while the denominators are increasing by 1. and the denominator is always 2 greater than the numerator. From here, we can get the next three elements of the sequence as 6 over 8, 7 over 9, and 8 over 10, which, given limited space, I'm not going to reduce to lowest terms right here. The explicit formula for this sequence can be written as a sub n equals n over n plus 2. You can see the pattern by just looking at the ones that came before it, like a sub 6 equals 6 over 6 plus 2, or a sub 8 equals 8 over 8 plus 2. Although both the numerator and denominator have their own skip patterns, this is not going to be either an arithmetic or a geometric sequence. And that's okay. When defining the nth term of a sequence, sometimes we can define the value of the nth term explicitly, meaning that there is a straightforward formula that can be used to determine each term of the sequence. Here are some examples of explicitly defined sequence, and you're asked to find the first 5 terms of each. If our sequence is defined as a sub n equals n squared plus n, then all we have to do is plug in values for n to evaluate the expression. The first term, a sub 1, is going to be 1 squared plus 1, which equals 2. The second term is 2 squared, or 4, plus 2 equals 6. The third term is 3 squared plus 3. 3 squared is 9, and 9 plus 3 is 12. For a sub 4, we have 4 squared plus 4, which is 16 plus 4, or 20. Finally, for a sub 5, we have 5 squared, or 25, plus 5 is 30. This example again is neither arithmetic nor geometric because although there is going to be a pattern in the skips, it's not a consistent difference for what's being added to each term, nor is it a common multiple or common ratio being multiplied to get from one term to the next. In this second example, we have a sub n equals 64 times 3 quarters to the nth power. Now with this one, you have to be careful because you don't want to try to simplify this expression as 64 times 3 quarters to get 48 to the nth power. The order of operations requires that we take 3 quarters to the nth power, then multiply that result by 64. This makes the first value, a sub 1, being 64 times 3 quarters, which is 48. A sub 2 will be 64 times 3 quarters squared, or 48 times 3 quarters, which will be 36. The third term will be 3 quarters of that. 3 quarters of 36 is 27. As we get to the fourth and the fifth terms, the numbers will get a little uglier. So we have 81 over 4 and 243 over 16. This will be an example of a geometric sequence because each successive term in the sequence is 3 quarters of the term that came before it. That value, 3 quarters, is referred to as the common ratio in the geometric sequence, which again we will get more into in section 12.3. Alternatively, we can define some sequences implicitly or recursively, where we will identify the starting value of the sequence, also known as the seed value, then describe a way to get to the next value of the sequence based on the previous term. Let's say we want to find the first 5 terms of an implicitly defined sequence. Remember, as we stated before, in an implicitly defined sequence, the first term must be given to you. So a sub 1 equals 2. The implicit rule given here suggests that the nth term of the sequence will be 3 more than the one that came before it, which would make a sub 2 equals 5. We can continue along this pattern to get a sub 3 equals 8, a sub 4 equals 11, and a sub 5 equals 14. Now, we could define this sequence explicitly if we wanted to. The key is that we see a consistent skip pattern in that every term is going up by 3 every time. This suggests that our explicit formula should have 3 times n as a part of it. However, if we left it as 3n, then our sequence would look like 3, 6, 9, 12, 15, but our sequence has values all one less than that, 2, 5, 8, 11, and 14. To fix this, we can modify the formula to say a sub n equals 3n minus 1. Now, the example we just did could have either been written explicitly or implicitly, but not every sequence can go either way. It's also possible that the formula one would use to describe the sequence explicitly is going to be so complex that it might not be worth trying to convert it from implicit form to explicit form. Here is one such example. We have a sub n equals 1.005 times a sub n minus 1 plus 200, where a sub 1 equals 1000. This is an example of something we call an annuity, where we might be adding money consistently into an interest-bearing account on, let's say, a monthly basis, and the interest keeps getting compounded along with every deposit. In this case, we're starting with $1,000 in the bank and adding $200 to the account every month, and the account is earning 0.5% interest each month, which, if you multiply that by 12, translates into 6% annual interest compounded monthly. What makes this different from regular compound interest type problems? Well, let's look at what's happening. In the first month, we have $1,000, but by month 2, we've earned 0.5% interest on the $1,000, which is $5, and then we add $200 more to that, which is a balance of $1,205. The next month, we have 0.5% interest on the 1205, then add $200 to that, which now gives us $1,411 and 2.5 cents. After that, we can take 0.5% increase on the 1411.03 and add that to the $200 to get $1,618.08. And this pattern is going to continue each month. What we see is happening here is that by compounding the interest more frequently, the amount we get in interest is increasing every month. The explicit formula is pretty difficult to deal with, so we're much better off leaving this as implicitly defined. So now we're going to look at something called a series and partial sums. Here's our definition. Given the infinite sequence, listed as a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, the sum of the terms a1 plus a2 plus a3 plus a4 all the way through plus a sub n and beyond is called an infinite series, or just a series. A partial sum is the sum of the first n terms of an infinite sequence. So a1 plus a2 plus a3 all the way up to the point a sub n. This is also known as a finite series, or the nth partial sum of a series, and is denoted with a capital S and a subscript n. Let's look at some examples. For the given sequence, find s sub 2, s sub 4, and s sub 6 for the following sequence. S sub 2 is defined as the sum of the first 2 terms of the sequence, which will be 3 plus 6 equals 9. S sub 4 will be the sum of the first 4 terms of the sequence, which adds up to 30. S sub 6 is the sum of the first six terms, which although I don't have six terms listed, the sixth term is pretty easy to compute once you see the pattern. Adding these up, we get a total of 63. Here's one to try on your own. Just like we did in the previous slide, we want to find S sub 2, S sub 4, and S sub 6, which represent the sum of the first two terms, four terms, and six terms respectively. You should pause this video for a couple of minutes in order to evaluate this. So here, S sub 2, also referred to as the second partial sum of the series, is negative 2. S sub 4, also called the fourth partial sum of the series, will be negative 20. And S sub 6, the sixth partial sum, will be negative 182 once we realize that the sixth term in the pattern will be negative 3 times 81 to get negative 243. Here's an example of the same idea, but this time we're not given the terms of the sequence, but rather we're given the formula for the sequence and asked to compute S sub 2, S sub 4, and S sub 6. The formula is one we worked with earlier, a sub n equals n squared plus n. And again, we want to find the sum of the first two terms, four terms, and six terms. But we're going to have to list them off before we can do any addition. Since we worked with this sequence earlier, I'm not going to spend a lot of time showing where these elements came from. I believe it's safe to say that at this point, you should be able to evaluate these terms on your own. From there, we can add what we see. S sub 2 will be 2 plus 6, or 8. S sub 4 will be the sum of the first four terms, which will be 40, and S sub 6 will be the sum of the first six terms, which is 112. A shorthand notation used to describe finite series and infinite series is sigma notation. The notation allows us to describe what values of the sequence we wish to sum up. For example, suppose what I'm here looks like so. That funky looking bent E is actually the Greek letter sigma, capital sigma to be more specific. And in algebra, we use it as a shorthand to describe something we want to take the sum of. We also can refer to that Greek letter sigma as a summation sign. To the right-hand side of the sigma, we see the formula, in this case, 3k. The k is for the index variable, and in most problems involving sigma notation, the standard is to either use I, j, or k as an index variable. Sometimes we will also use n, but more often than not, we prefer to leave n out of it in case it's needed later. Right below the sigma, it says k equals 1. This tells us we're going to start our values of k at 1, and at the top of the sigma, we see the number 5, which suggests that we want to go up to k equals 5. Putting this all together, what is implied by this notation is that we want to substitute k equals 1, then k equals 2, k equals 3, k equals 4, and k equals 5 in for k into the expression 3 times k, then sum up the five numbers we get. This expression is read as the sum from k equals 1 to 5 of 3k. And we're going to evaluate it by taking 3 times 1, then 3 times 2, then 3 times 3, 3 times 4, and 3 times 5, and adding the result. Multiplying these out, we get 3 plus 6 plus 9 plus 12 plus 15, which add up to 45. Let's try another example. Here we have the sum from k equals 1 to 6 of the expression 2k minus 1. Our strategy is going to be like before, where we will plug in all of the whole number values starting at k equals 1 and going up to k equals 6 into this expression, evaluating each term, and then taking the sum. Why don't you try this one on your own, and we can pause the video for a bit to let you get this one a try. All right, here we go. Plugging in the values gives us 2 times 1 minus 1, then 2 times 2 minus 1, 2 times 3 minus 1, 2 times 4 minus 1, 2 times 5 minus 1, and 2 times 6 minus 1. Evaluating each piece will give us 1 plus 3 plus 5 plus 7 plus 9 plus 11, which adds up to 36. This one is a bit more complicated because it has two pieces to it. We want to take the sum from k equals 1 to k equals 6 of the expression negative 1 to the k power times the fraction k over k plus 2. The strategy is the same as before. We want to evaluate the expression for each whole number value of k between k equals 1 and k equals 6. What the negative 1 to the k power will do will make the sign value of each term change from negative to positive or positive to negative every time. When the expression has alternating signed terms going back and forth between positive and negative to positive, we call that an alternating sequence. Let's look at what happens in the process. So we have negative 1 to the first times 1/3 plus negative 1 to the second times 2 over 2 plus 2 plus negative 1 to the third times 3 over 3 plus 2 plus negative 1 to the fourth times 4 over 4 plus 2 plus negative 1 to the fifth times 5 over 5 plus 2 plus negative 1 to the sixth times 6 over 6 plus 2. Simplifying each term, we get negative 1/3 plus 2/4 minus 3/5 plus 4/6 minus 5/7 plus 6 over 8. If we use our calculators, we will end up with a pretty ugly decimal, but our calculators can also convert that into a fraction, which will reduce to 617 over 420. One thing that I will note at this time is that you can do summations like this on your graphing calculator. If you have a TI-84, there is actually a sigma command that you can be using. And if you have a TI-83, the syntax is a little bit trickier, but it is there. Be sure to remind me in an upcoming ORT session, and I will set up my graphing calculator emulator to show you how this is done. Now, in some of the problems on the homework, you're given the sum and asked to work backwards to translate that into sigma notation. Here's going to be a few examples. Suppose we're given the expression 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and we're asked to turn that into something with sigma notation. The first thing we need to do is write out the big sigma. Since there are 5 terms in the sum, we'll start at k equals 1 and continue to k equals 5. Each term in the sum appears to be 1 over a number, and the values in the denominator are all increasing by 1. You might look at this and wonder how the first term is going to work, but if you look at the number 1 as the fraction 1 over 1, it will be easy to follow the pattern just as in our other terms. So our final answer is going to be written like so, with the 1 over n after our summation sign. Here's another example. 2 minus 4 plus 6 minus 8 plus 10. Again, we have a sum of 5 terms, so we can, just like we did before, write our summation sign with the big letter sigma with k equals 1 at the bottom and 5 on the top for the 5 terms. Since the terms are changing signs every time, the terms are following that alternating pattern. And the way we dealt with that on the previous slide was to introduce a factor of -1 to the k power that would get multiplied by our expression. The problem with that, however, is that if we left it as -1 to the k power, you would have the first term be negative, the second term be positive, and then the third term would be negative, and so on. That's going to have all of the signs backwards. So to fix this, we're going to take -1 to the k plus 1 power, so that for the first term, when k equals 1, you have -1 squared, which is positive 1. For the second term, you will have -1 cubed, which is -1. Typically, when you see in a sequence or a series that the terms are alternating, you will want to have either -1 to the k power or -1 to the k plus 1 power in there, depending upon whether your first term is negative or positive. As for the rest of our terms, they're all multiples of 2. So we can just put in 2k for our expression, and we're done. Here's one more to try. Let's pause for a minute to see if you can figure out this one on your own. Let's start with the summation sign. This expression has 6 terms in it, so we're going to write the summation as starting from k equals 1 going up to k equals 6. Some of you might be thinking that the fact that each term is double that of the term that came before it, that we might want to write something in implicit form that addresses that. Unfortunately, when working with sigma notation, you always have to write your expression in explicit form. In this case, each term is a power of 2, starting with -1, such as 2 to the 0 power, and working your way up to 32 as 2 to the 5th power. Since what seems to happen is that the exponent is 1 less than the value of k that we want, we can write the expression as 2 to the k minus 1 power. Here's the problem challenge problems for section 12.1. Go ahead and give these problems a try on your own. By this point, you know the routine. We'll be going over these problems in an upcoming ORT session, and the answers are in the back of the book. If you have questions on them before we go over these in class, you can email them to me, or better yet, you can post them on the general questions and items to share discussion board. Thanks for watching, and we'll see you all soon.